So the next section we'll be covering is section 2.5, which is the fundamental theorem of algebra, a pretty large result and quite the name. That being said, we're not going to do too much in this section. Really, the main result is that we can write a polynomial as a product of linear factors, which we'll see in a moment here. And also, we're going to talk a little bit more about complex roots and what we can do with complex roots in a polynomial, kind of to connect back to section 2.4. So the first thing I want to write down is the fundamental theorem of algebra. Now this does have a couple different variations, but the big result that we're going to be using, and the one that I want you all to sort of internalize, is that every single variable polynomial, that part isn't so important. That just means all it is x, f of x, rather than f of x and, say, y or something, with degree n, and it has complex coefficients. Now keep in mind here, I do want to pause just before I continue. When I'm saying complex coefficients, we've been dealing with polynomials that have real coefficients, and remember, real numbers are actually part of the complex number system, so it also applies to polynomials with real coefficients. That will apply more to us. So every single single variable polynomial, let's just go ahead and remove the double single there. Every single variable polynomial, so that's one keyword, with degree n, and it has complex coefficients, or really real coefficients. Here's the big result. This polynomial has exactly n complex roots. And that includes potential multiplicity. So if we count roots more than once, that also applies here. So for example, if I just wrote any random polynomial down, I did not come up with this previously, I don't know what the roots of this are. Oops, that's weird. So if I just threw this polynomial at you, you might not know what the roots are, but you can say that the polynomial has 7 complex roots. Now some of those might be real, all 7 of them might be real, but we know it has 7 roots. So what we often say here is that the complex numbers, in a way, they sort of complete the number system, right? The real numbers are sort of lacking because we can't solve every single equation involving x's. We have that square root of negatives that come up, but the complex numbers are really powerful because they essentially complete the number system, and now we are totally able to solve every polynomial we come across. As an additional statement, we can then rewrite every polynomial as a product of linear factors. This means that we can basically just factor a polynomial, right? So that polynomial I had up there, f of x, I don't necessarily know what the roots are, but I know that if I have, let's call them root 1, root 2, all the way to root 7. So in this example, I'm saying that R1, R2, these are the roots. And so up here where I said every polynomial, I should also mention that if this is degree n, then it would be n linear factors, right? So this was 7 linear factors in this case. So beyond actually rewriting polynomials in terms of their factors, we're not going to deal too much more with this theorem. It's really just a pretty big result, and it's really intended to show us that the complex numbers are super cool and they complete the number system. Now, in order to just kind of give you further examples of rewriting this as roots, I want to talk more about complex numbers now. So let's go ahead and talk a little bit more about complex roots, and then I'll relate this back to what we just talked about, rewriting a polynomial in terms of its linear factors. So the first big result that I want to mention is any time you get a complex number, let's call it z, and I'll write it in its standard form as a 0 to a polynomial p of x, then its conjugate, remember this changes the imaginary part to negative or vice versa, negative to positive, but the real part stays the same. But if you have a complex number as a 0, then its conjugate is also a 0. This is another big result. Okay. So here's what we're going to do with this result. Let's just say that, let's do this. Okay. Let's go ahead and determine the equation of a polynomial. Boy, I'm writing a whole bunch today. We're actually getting into an example now, though. Before this was mostly theory. So determine the equation of a polynomial with roots, let's say 2 and then -1 plus 3i. And I'm going to say that you can leave it in factored form. For now, we will adjust that a little bit later on. Okay, so here is sort of a typical example you might run across now that we've gotten through all this theory. All right, so let's go ahead and pick a letter for our polynomial. I like to use p for polynomial. P of x equals, now each of these roots has to have a linear factor. So it's going to be x minus 2. And then I'm going to have, this one's going to be a little bit strange. I'm going to go x minus, now I have to write this complex number in here. But this is not complete yet, because if this shows up, so notice z is here, we also need its conjugate, which would be -1 minus 3i. So I'm going to include one more factor, x minus -1 minus 3i. So here we use the fact above in order to get our last factor. And I said you can leave it in factored form, so this would be done based on this problem. So this part was really just to illustrate that once you get one complex root, you can always get another one. Let's take this a step farther now. So let's go ahead and let's do an example let's do this. Rewrite p of x from the above problem in general form. So remember, that means we have to write it as a sum of different factors, monomials, not factors, and the largest exponent of x has to go first. So here's what we're going to do. I'm going to show you all a way that we can sort of use the structure of complex numbers to help us out. So I always start with the complex factors. Now keep in mind, if we're rewriting it, we really have to distribute everything, right? So we have to multiply and then multiply some more and then keep doing that until we end up with the correct format. But I like to start with the complex factors, x minus -1 plus 3i, and then x minus -1 minus 3i. Now this still doesn't look great because technically I would have to do x times x times -1, and then x times that one, and then I would take -1 times each of those, and so I'd actually end up with 9 terms. But like I said, we're going to make use of structure here. So what I'm going to do is pretend like this is just a binomial, two binomials being factored, and so I'm going to, distributed, and I'm just going to multiply these together first of all. So x times x will give me x squared. Next, I'm going to have -1 plus 3i x. Let's keep going with this. And then for the last one, I'm going to have these multiplied together. Okay, so it doesn't really look great. However, there are a couple of facts we can make use of. First of all, this is z times its complex conjugate, and we had a formula for this. It's a squared plus b squared. And so this is just going to be -1 squared plus 3 squared, which is going to be 10. So that's super helpful. Now the next thing I want to point out is I will have to distribute this negative to both terms in here. And we're going to get some more cancellation. So let's go ahead and clean this up just a little bit. I still have my x squared, but now I have plus 1x. So I took this, and then I have another plus 1x. And then I'm going to have a -3ix, which looks not great. I don't know what 3ix really means. But what's nice is this is actually going to end up being a plus 3ix. So notice these imaginary terms are always going to end up canceling out to 0. And then finally I have that plus 10 that I figured out over there. So combining like terms, we do end up with plus 2x plus 10 here. So this was a little bit involved, but as you start to see the pattern, as you do more of these, it will become a little bit easier. Just know that the imaginary part should cancel out. And then also we can use the fact that I used up here, that the complex conjugate times the complex number is a squared plus b squared. So it's x squared plus 2x plus 10. Now I'm not quite done because the polynomial was x minus 2 and then x squared plus 2x plus 10. So we do have to go one step further. We're going to go ahead and multiply this. Just kind of regular multiplication here, no quick tricks or anything for me. And so I end up with x cubed, the 2x squares are equal to 0, 10x minus 4x, and then minus 20 is my final polynomial. So these problems do take a little bit of work. They don't come super easy, and you do have to sort of persevere through them, make use of some structure. There's some really great mathematical algebraic manipulations going on here, which I love. So please don't just give up on these problems because I know they're long. Take your time with it, use the structure, and use what you know about multiplying polynomials. And that concludes section 2.5.